Good evening, everyone. I hope I'm audible. My name is Tazeen, and this is your seventh lecture of NPTEL course, Geographic Information Systems. And today we will be discussing about the same module, which is the second one, that's real world to digital world through GIS. And we will be briefly covering about data models, objects, grids, how we are going to use them, and attributes related to them. So this is where we are in today's session, that is week 7. We are talking about the quality of data and database, and we are trying to introduce to you data models in more detail and how certain basic parameters of data model are relevant, and you're going to use them while you are preparing your data models. So let us quickly brush up through last week's summary. So last week we have learned about the process of converting a real world model into a data model, where we have a certain geographical location and how we are using our tools of GIS and our geospatial information through satellites and imagery, and how we are converting it to a data model. Then the flow of a real world model, which involves the movement of information. So we are transferring a real time, real life information that exists on the Earth's surface into our processing system, and we are trying to get an output that is parallel as well as it coincides with what is available on the surface of the Earth. So from the actual world, we are taking it to the analysis phase. So in a real world model, entities are classified based on their kind, and they possess attributes and relationships. So we try to understand the basics of these attributes and relationships. Next, we understood that geographical data may be divided into two basic components. First is the geometric data, and the second is the attribute data. In a geometric data, we are trying to correlate the data with the spatial characteristics of a particular element or variable that we have. And in the attribute data, in which we provide additional information about the same variable or the same entity of which we are spatially trying to convert it to the digital model. So when we are considering these attributes, they can be measured on several scales. We discussed nominal, ordinal, interval, and ratio scales, which are very basic and which were very simple also. I hope they were understood by each one of you clearly. Next, we got to know that the connections between entities may be categorized into four main types: belonging, comprising, locating, and bordering. We also understood that the user's text does not contain any information to rewrite. So what happens that in a subsequent session of GIS, we delve into the functioning of the data model rather than going to its characteristics. Now let us discuss last week's assignment, which is assignment 6. We come to the first question where we are talking about space segment. So in a space segment, there are dash orbital planes spaced dash apart and inclined at about dash to the equatorial plane. So the correct answer here is the space segment has six orbital planes, and they are spaced at 55 distance apart and inclined at about 60 degree to the equatorial plane. This was self-explanatory from the lectures of previous class from Professor Bharat. The second question is the electromagnetic region used in GPS signals is visible, thermal infrared, radio wave or microwave. So in this case, the electromagnetic region uses GPS signals in the form of microwaves. Although it is self-explanatory, we have radio wave also, but radio wave actually falls within the microwave wavelength. So GPS signals primarily use microwaves for communication, where the L band frequency is 1.5 gigahertz. So the appropriate answer will be microwave. If we further want to, so for communication, microwave is what we are using. But if you need it for a specific task, then we further go into shorter categorizations, and then radio wave will be the answer for certain specific other functions, not for communication. Which of them represents the ideal geometry of satellite for obtaining perfect location details? So the answer here will be the option 1. So what is happening is all the orbits are aligned with the satellite. So in this case, what is going to happen? This kind of satellite geometry or arrangement will actually give you the perfect location details. But in other cases where they are present in only one single orbit, whether it's outer or inner, it is not possible for you to obtain the perfect location details. Question number 4. Which of them is not an error associated with GPS? Geometry of satellite orbit, radiometric, atmospheric propagation delay. It is very straightforward from previous lectures. The answer will be radiometric, because the other three options, that is geometry of satellite orbit and atmospheric propagation delay, are errors associated with the GPS. Fifth, benefits not associated with WAAS, WAAS are provides accurate navigation signals, precision approach for an airport to at lower cost, enables aircraft to avoid lower altitudes and fly at higher altitudes, cost-effective alternative to ground-based systems. So in this case, the correct answer is enables aircraft to avoid lower altitudes and fly at higher altitudes. So this is not one of the benefits that is provided by WAAS as well, whereas the other three options are the benefits provided by WAAS. Question number 6. Which of the following GNSS does not serve Asia? All three, that is GZSS, Compass 2020 and GLONASS, all three does serve Asia. So none of the above is the answer. Question 7. IRNS is a constellation of dash satellites and ground station that serves dash 7 worldwide, 6 Asia and West Pacific, 7 Southern Asia. So the correct answer is C. It is a constellation of 7 satellites and ground station serves Southern Asia. Which of the following is not a member of GNSS provider? Japan, China, Russia, Germany. So the correct answer here is Germany, because these are your satellites associated with it, that is GPS, GLONASS, Galileo, PDS, QZSS, INNSS and SPAS, and all of these are belonging to mostly the South Asian and United States countries. So Japan, China and Russia fall within these operating countries, but Germany is not a part of it. Maximum amount of errors caused in GPS signals due to dash, multipath, receiver noise, ionosphere delay, ephemeris. So in this case, the maximum amount of errors caused in GPS signals is due to ionosphere delay. The reason is the ionosphere delay, which is also known as the ionosphere refraction, is a phenomena that affects the propagation of radio signals as they pass through the Earth's as ionosphere. So in this case, this is the most impacting element that causes errors in our GPS signals. What happens in case of ephemeris? In case of ephemeris, it provides the predicted positions of celestial objects such as satellites or planets at specific times. So this does not have a relation with our GPS signal. It is giving the position of celestial objects, that's satellites, planets, etc. Okay. Multipath is also an error, but it does not have as impact as the ionosphere delay. Number 10, errors caused in GPS signals due to adjacent buildings are termed as multipath. Okay, so multipath is another error as I've already told you, but this is caused due to the adjacent buildings that are present on the surface of the earth rather than the ionosphere, where actually the refraction causes a phenomena of distracting the radio signals that is more massive. So therefore, in this case, the answer is multipath. You have already understood ephemeris. So let us understand the outline of today's short session that we have. We will be starting with a more depth knowledge of data models. We will try to understand objects and its characteristics, and we will be talking about the graphical representation of these objects, followed by layer grids and object attributes. Some of these basic outlines have already been introduced to you in the previous lecture, but we will be talking more in depth in today's session. So we have already understood a basic layout of a data model. It is nothing but how the real world model or the real representation of what is present on the Earth's surface at a specific geographical location in a certain time frame can be represented digitally in the form of a data model through GIS. So a real world model enhances the examination of a specific domain of application by decreasing the complexity that are taken into account. So this is again a graphical representation of how you can understand a data model. So this is how your real world looks. This is a farmhouse scale. This is your landscape scale. So this is how this is represented in the form of a terrain model. Then you see there are different land units, and it is a form of cluster analysis that actually gives you different clusters or different categories that form this farm scale at a digital level. So you have several layers like your water content, your solar radiation, your digital elevation model that gives your terrain, the land cover that gives the different types of specifications of the land that is present there, and your aerial photograph that is your actual imagery that represents your real world. So in order for a real world model to be deemed useful, it is essential that it be implemented inside a database. So one of the most important factors about having a digital model is the use of database model, which facilitates the achievement of a feasible outcome, but that is possible only when you are maintaining a certain database and you're careful about your handling of metadata at different servers like cloud services or even at manual digitized version of your databases. So the manipulation of geometric entities such as points, lines, regions or polygons or areas is a common practice in data model. This is what our data model is comprised of. If it is a vector model, it will comprise of points, lines, regions, areas, polygons. If it's a raster model, it is going to have several number of pixels. So these entities serve as bearers of information inside data models and are often referred to as objects. So if you see the figure on the right, so let us look at the first figure. You have seen this figure before in a different version. So let us again try to just brush up what we have seen it earlier as. So this is your real world. On top of that, we see a raster layer of land use. So here there are different pixels or grids that form different sections of your raster digital model. Then again we have a raster plane which gives us the elevation of the real world. Then we have a vector version of our real world where the parcel of land division is represented in the form of uh, polygons. Then we have streets. Our streets are represented in the form of lines as well as polygons, which again represent a part of the real world, as you can see in the bottom. And your point uh, feature of vector digital model is representing the customers or the movement of people or the number of people residing in that particular real world area. So these entities serve as bearers of information inside your data model and are often referred to as objects. Okay, so these are different planes of objects. Similarly, if you try to analyze the model on the right hand side or the figure on the right hand side, this is now a digital representation of your data model. So a data model is a digital representation of your real world, but this particular image is a digital representation of the data model. So what is it showing us? This is a data warehouse. Okay, so this is where we have a collective uh, repository or inventory of all the data sets that is available to us. Then we have a column lineage. So what is this column lineage? It is actually telling you the flow of the database, the linkage or the connectivity of the database to one another, that is from one object to the other object. Then you have a table lineage. So this table lineage represents the attribute data of your data model. Then you have a modeling layer. So modeling layer tells you what are the different layers that comprise the total model. So as you are moving up the hierarchy, it is clustering your data and the objects within the data model. And finally you have the business layer. So it's not exactly a business layer, this is just a dummy diagram which is for business module. So in case instead of that, if you're working with urban planning models, you might have to replace this. Instead of business layer, it might have your urban dynamic layer, something like that. Okay. So in the context of your data models, objects represent items found in the real world models and are seen as a database representation of real world phenomena. So here again we can see that several objects form your entity, and this entity is a basic carrier of information. So here we are talking about the smallest level of your database information, which is an object, and collectively a lot of objects combine together to form an entity. So objects can be defined by entity and it can be characterized by several features. We have categorized five of them here, which are standard. So first is the type. Type you can categorize based on the unique ID. So if there's an FID or UID which is present in your attribute table or your metadata. So if you can identify that ID, you can categorize your type, or you can also categorize it with the help of a text. Let's say instead of giving it an ID, I have given it names. Okay, that this is there are different data, and one is Delhi, then there's Noida, there's Faridabad. So I have given text type to my objects. Then you have your object class. So if I'm doing a land use land cover, then maybe several object classes can be identified from there. So one is your green cover, then you have your barren land, you have agricultural fields, you have water bodies, you have built up, so and so. Second type of characterization that is possible is your attributes, which can be qualitative or quantitative. This we have already talked about in the previous class, so I'll just give you a hint of it. If you are talking about qualitative, it is mostly associated with the non-metric or non-numeric data. If you're talking about quantitative, it is any form of numeric data. The third identity characterization is your relations. So relations are calculable and they are attributable. So what does this mean? It means that the relations can be computed. For example, I have a certain polygon and that polygon has certain quantitative data associated to its attributes and different object classes. Okay. Now what I can do is I can create a relationship among those, and I can actually from that polygon. So let's say I have line data. I have the thickness of the line. I have what it represents. Maybe it represents a bond. So I can calculate the area of my object, right? Sorry, the entity or object also. So let us say there are 16 ponds in my study area. So we are talking from the perspective of urban planning. So if there are 16 ponds, so every pond will have its area, correct? So we have instead of calculating the area, let us assume that the area data is also available in our attribute table. So we have the perimeter of our ponds, we also have the area of our ponds, we have the the depth of the pond. So what we can do from this data is that when we are talking about relations, we can actually calculate that out of these 16 ponds, how many ponds are having area more than, let's say, 25 square meters. Okay, this is just an assumption. So we can calculate that, okay, out of 16 there are 10 ponds that have area more than 25 square meters, right? Similarly, we can also calculate the volume of these ponds, that how much water holding capacity does each pond have, right? So your relations of different objects within your entity, so they are calculable. We are able to calculate new attributes or new features from them. Fourth defining characterization is your geometry. So geometry is nothing but it's simply your point, line, and polygon. So if let's say in an urban area we are trying to identify a road, so we identify it from its geometry. So we say that, okay, all the line segments in this particular thematic mapping belong to the road category, right? If we are having any so let us say there are several line typologies. Okay, let us take that example. So what happens when we are representing our road rail network as well as the uh, metro lines with line, right? So all these three categories are being used by the geometry line. So what do we do in this case? We actually define each of these geometry further. What we do is we say that, okay, the gray line geometry is representing our roads, the brown ones are representing our rail network, and the maybe red ones are representing the metro line. Okay, so this way we are further defining the geometry, so that same type of geometry do not create confusion for the user. The fifth identifying characterization that we are talking about is the quality. Now, the quality of any object is very important, just like the quality of the database is important. What does it mean? It means how accurate is your, you know, object identification or object characterization. Okay, to what extent it is, how it is being represented, right? So, for example, if we come back to the pond example, how accurately does your pond geometry, pond relation, and the typology represents the real world pond that is there, right? So the quality of your entities also matter a lot. These are just a few examples where you can see how a unique ID, so an address or a pinpoint geographic location is represented by the unique ID type. Then the relationship of polyline with polygon. So this is a polyline or a line. So let us say this is some piece of land. So let us say this is a forest land, and this is the defined boundary of the forest land, and this polyline that is passing through it is some river. So this is how your relationship is being defined. In your geometry, you have very well understood how points, line, and your polygon in the form of area regions are represented, and the quality, which is how purely it is defined by the real world entity. In a real world model, the entity and the entities that we are defining through these real world models cannot be directly implemented in databases due to the fact that a single entity might consist of several items. This is very much possible even when we were defining a pond. We had 60, right, instead of just one. So an example of this can be seen in the representation of the entity Shalda. So Shalda is nothing. Shalda is a railway station, and Shalda is also the region. I'm not sure how many of you are familiar. So this is composed of multi-ways. Okay, so this should have actually been here. I'm so sorry. It's been pointed at a farther location. So if this yellow dot would have been here, we can see that it is a multi-roadway section between intersections. This is a major cross section of that particular region. So each of them have a defined object information. Each of your intersecting line will have a defined information about that specific object. So what does this indicate? It indicates that the selection of information carrying units and their magnitudes is necessary prior to entering the information into your database. So you have to be very careful and very precise when you're entering your information into the database. Similarly, the criteria for dividing a roadway into sections must be determined before the roadway can be accurately described. So if you initiate your database in the wrong format, or if you have a precision issue, it is going to create a wrong assumption as well as wrong analytical results, leading to a wrong decision making based on your data model. Now there are types of codes that are based on object classification. So whenever we are talking about object classification, we can uh, transfer them. Okay, so we can transfer them from entity classifications, and an object may be classified under one type code only. So your each object has a unique code. So data models may be designed to include physical objects. So when we are talking about physical objects, they might include roads, water mains, and properties. Classified objects, these are the types of vegetation, climatic zones, or age group. So what is happening in a physical object? We are talking about something that is tangible. Okay, that means it is physically present in the real world. But in classified objects, we are defining the type of vegetation. It may or may not be tangible. So when you are defining the type of vegetation, vegetation typology can be tangible, but if you are talking about climatic zones, it is not tangible. You can't really touch winter, correct? You can't touch winter, or you can't touch spring. Or if you talk about, let's say, age groups, you can't touch age group, but you can actually touch a human, right? So you're not directly touching your classified objects. But in terms of physical objects, they are tangible and you can physically feel them. Third is your events. So what happens? Events, again, these are accidents or water leakages. So events are some sort of condition that leads to a certain type of activity in a particular region. Fourth is your continuously changing objects, right? So continuously changing objects are associated with earth phenomena, correct? So this may be your temperature, it can be your precipitation, it can be your urban heat island effects, right? It can also be your evaporation or transpiration, correct? And the fifth one are your artificial objects. Now, these artificial objects are very keen and they play an important role when we are making data models, like elevation contours. So, this particular map, this shows your elevation. contours, but these are not actually present on the surface of the earth. These are artificial objects, but these help us determine a lot of other events or phenomena that are happening from 1 to 4 based on these artificial objects. Another example of artificial object is your population density, right? It is not actually present in the form of some element or some, it is not even a part of some any event or something, but these are calculated so that we can better understand the other types of objects that are affecting it, or maybe this one is affecting the other objects. For example, population density might affect your waterways, right? It might lead to a higher level of water pollution. Just an example. So artificial objects for a selected representation and database in the form of are represented in the form of raster. Correct. This is again another example where this is a digital elevation model. Then this is your terrain model, and then finally you have this, what to say? It's like an elevation map. So this different color codes represent the highs and lows, which you can actually generate from the eyes. But both of these, whether this or this, is actually an artificial object. Now we come to graphical representation of objects. So we have already understood that graphical information on objects may be entered in three terms, right? First are your points, which are these. Second are your lines, and the third are your polygons. Now, when I be talking about points, we are trying to represent it as single x or y coordinate, correct? And it has zero area. That means points have no dimensions. When we are talking about lines, so in case of lines, two or more connected xy coordinates are representing lines in only one dimension. These have a particular dimension, right? So they have single dimension. So they are represented in 2D. Then we have the areas or the polygons. Here, three or more ordered xy coordinates form a loop. So this is two-dimensional. Sorry, this one is one-dimensional, but this one is two-dimensional. But if you go in the z direction, including the area part, you go into the three-dimensional version, which has a different purpose, but that does not have a direct link to the basicity of graphical information of your object. That also has a link because but it doesn't have a separate entity, as in points, lines, and areas. These are your basics. From the areas, we go to the 3D, correct? So 3D does not have its separate base identity. They derive from these three only. They are deriving from your areas, right? So let us discuss about points in a little bit more detail. So in a geographic information system, which is GIS, a point refers to a single geographic location specified by its coordinates, usually in terms of latitude and longitude, or in a projected coordinate system such as UTM, right? So if you look at this diagram, here you have a multi-point input. So you have multi-point A and you have multi-point B. But after putting this multi-point input in your GIS, this is the type of output that you get, which is in the form of points. Another example is if you look at this point, so as the definition says, it represents your latitude longitude. So if we just assume them to be latitude longitude on this graph, we see that it is pinpointing pointing to a certain geographic location. So pinpointing means it's either the location of a human or a tree or a house or any other object. So a point is defined by its x and y or latitude or longitude coordinates, and it represents a single point on the Earth's surface. Points are fundamental elements in GIS data and are used to represent discrete features such as specific locations. So it can be maybe a home address, events or incidents. So maybe this was the epicenter of an earthquake, right? Then it can be sampling or monitoring sites. So this is maybe the origin of my mining site, origin or destination. So maybe this is from where my journey started or or where my journey ended. It can also be a geographic feature with no area. Maybe there is a tree which is 100 years old and it has this specific location on the Earth's surface. Now, if we talk about lines in a GIS system, a line refers to a type of vector geometry used to represent linear features on a map. So, what is happening? Whenever you are taking a line, you are connecting a series of points, right, in a specific space or in a specific area. So, this represents features such as roads, rivers, boundaries, or any other linear entity. So here are some key characteristics of a line in GIS, but before we move to that, let us understand this. So this is like a multi-part line, right? So this multi-part line can be represented in this form in your GIS. And whenever we are talking about a line, it means two points are being connected, two or more points. So geometry, your geometry plays a very important role because we are talking about vector entities with respect to objects. Your attributes, so what is the length of the line, what is the thickness of the line, what is being represented by the line. Directionality, so whether I'm going from point A to B or I'm going point B to A is also very important. Then the typology, which is the thickness and all, the representation, how you are coding your line, right? Whether it's a river or a road or a boundary. Some of the examples of use which we have already understood. I hope it is now better in terms of apprehending these examples. So it's roads and highways, rivers and streams, utility lines like power lines, pipelines, boundaries like political boundaries between states or countries, railroads, trails, and pathways. Okay. The third type is polygons or areas. In GIS, a polygon is a two-dimensional geometry, right? In case of line, it was a single dimension. So this has a series of interconnected straight lines. So as we move up the hierarchy, what happens? The previous one forms a cluster and forms the other entity which is at a higher hierarchy. So line is formed by a series of points, and polygons are formed by a series of lines, and polygons are also formed by a multi-series of points, correct? So a lot of points collectively form your polygon, right? So it has the other two entities in it. So it is interconnected straight lines that form a closed loop. It is defined by a set of vertices, those are your points, and edges, those are your lines that connect them to an enclosed area. So this is your multi-part polygon, and this is how the output comes if you are feeding it in GIS. And similarly, so your polygon or your area or region specifics have your points, and it also has your lines, and collectively they both form your polygons. So some of the key characteristics of polygons are a closed shape. If it is not closed, let us say there were three points, but there were only two lines with an open edge. So one edge was open. So now it is not actually forming a polygon. It is still forming line, right? So for any time for it to be a polygon, it needs to have a closed shape. So whenever it will have a closed shape, it will have an area, right? It will also have vertices, like this one has three. It will have edges. This one again has three. It will have attributes, and it will have a specific typology. So examples of polygons in GIS might include land parcels, administrative boundaries, let us say a state or country that is being represented by the line, lakes, buildings, ponds, barren lands, agricultural fields, etc. Understanding and manipulating polygons is a fundamental aspect of spatial analysis in GIS, as it allows for tasks like area calculations, overlay operations like finding intersections between polygons, and various type of spatial modeling. So we will quickly take a 10 minutes break before we rejoin to finish this session. I will be back at 6:47. Okay, so let us get back to our discussion. So, moving further with the graphical representation of an objects, we have understood the following, that a point which has a zero-dimensional object specifies the geometric location through a set of coordinates. In case of a line segment, which is your vector data, a one-dimensional object, that is a direct line between two endpoints, is represented. A string, that is a sequence of line segments, is defined by this specified name, and it is also used in your GIS representation. Area or polygon has a two-dimensional object, and it is bounded by at least three one-dimensional line segments. So this is representing your point, you have understood. This is your line. But when you have a series of line, we actually call it as a string. And in case of this particular two-dimensional object, which is your area or polygon, we have minimum of three lines which are one dimensional. In case of raster cell or raster pixels, we have a two-dimensional object area that represents an element of a regular tessellation of a surface. So this is your raster area or raster cell pixel, that is representing a specific point on the surface of the earth. Now, if we understand grids, we will be talking about how we can divide the real world object into different format when we are creating our data model. Well, so whenever we are trying to objectify the real world model, we describe it by dividing it into regular squares or rectangles, so that all the objects are described in terms of areas. So this entire data structure is called the grid. If we take the example of this particular combination of images, we have contour lines that connect interpolated positions on the lattice frame. So here we have every point at different grid segments. Okay, so you can see that some of the points are located on the same grid, while there are grids that have only one interpolated contour point, right? So this is a grid segment that represents different point marks of a contour. Similarly, grid lines form cells with values at the center, right? So here you have the lattice position, and this is your grid, and these lattice lines intersect at those values. So your lattice point actually intersects at the center of the grid, which contains the value information. So considering this as your reference frame, this is a larger combination of a number of grids, so it has multiple grids, and this again, if we just take the small portion and we zoom in, we can see that it has several data values. So these data values are positioned at a specific XY coordinate that is represented by these yellow dots. Okay, so these are a combination of your grids and lattices with lot of data values. Similarly, if we take this same example in a three-dimensional figure on GIS, we see that the 3D grid display pushes each cell up to a level of stored value, right? So this stored value is actually telling us the height of a certain elevation. So let us consider this to be again a terrain value. So this is giving a three-dimensional picture of your contour. So what is happening, each of these grids that have their data values marked with these yellow dots again, we see that now in 3D all the grids are having a different height or a different elevation as per the value that is stored in them, and this particular representation is known as your 3D grid as blocky, and this is your 3D lattice known as smooth. So this is a smooth lattice, while this is a block grid representation. In case of 3D grids, we are seeing that each cell is being pushed up, while in case of 3D lattice display, we see that it pushes the node of the wireframe up to the value, correct? So whenever we are looking at the 3D grid, we are looking at the square boxes, but whenever we are looking at the 3D lattices, we are considering the center values that contains your data values only. So it is the intersection point of each of the grids. Now there are different types of grids that are used in GIS. The first one will be your raster grid, which is I'm sure quite common to you by now because you've heard this terminology several times from all of us. So a raster grid, also known as a grid cell or a pixel grid, divides your geographic area into regular arrays of cells. So what happens once it is divided into regular arrays of cells, each of these cells is assigned a value that represents a specific attribute such as elevation or temperature or land cover type, etc. This forms the basis for raster data, which is one of the primary data types in GIS, which has already been explained to you in detail. The second type is your vector grid. I'm sure you've heard of this vector grid as well because we have explained to you vector data several times. So in case of a vector grid, it uses a combination of lines or polygons or maybe just one single type of entity, and it defines a regular grid structure. What happens that in each of the line or polygon that is representing our vector grid, uh, it defines a grid cell. So one single entity describes one single grid cell, and they are typically used for discrete features that need to be represented as individual entities. For example, land parcels or sampling zones. The third type is your coordinate grid. Now, this is a new term which we have not discussed earlier. In case of a coordinate grid, it is used to specify locations on a map using a system of horizontal and vertical lines that form a coordinate reference system, which is your CRS system. What happens is that this particular system allows you to precisely position your features using coordinates. So a perfect example of your coordinate grid could be your latitude and longitude or your UTM coordinates. Next, you have your graticule. Graticule again is a new term for you. A graticule is a network of lines that represents meridians of longitudes and parallel of latitude on a map. So it will help you in navigation, orientation, and measuring different types of distances, right? So graticule is mainly used for navigation or orientation purposes where you have to do a certain level of measurement on your map. So you want to measure the real world distances, or you want to navigate on the real world model. So for that, if it's a longer distance, it is easier if you do it on the data model because you can digitally measure larger distances which do not have a limit. So if you just look at the figure on the right hand side, you can see that each of the grid cells here are being represented by some sort of uh, feature, and every feature is having a symbology or a legend associated with it. For example, the diagonal lines represent your residential land parcels. That means there are residential houses or buildings in these land parcels, right? Which are diagonally inclined towards the right. If it is diagonally inclined towards the left, which is these represent your forest. If you have a 180-degree horizontal line, it is agricultural land, as in this parcel. Whereas if you have a vertical 90-degree line, which is here, it is a commercial piece of land, whereas the solid covered land parcels are unmapped. That means we have not identified and classified them as any typology. So this is like an example of your raster grid data, correct? Then in the second example, again we are trying to show that what are the different features of this specific feature. So these are your rows, these are your columns, and each grid or cell signs is defined by these small parcels of measurements, correct? So the value attribute table that will be associated with this kind of grid data will give you the count of that data. It will also give you the features or types that are associated with that data, and many other attribute values that the user has assigned or that you want to assign to it. Next, we need to understand the different uses of grids in GIS. So, out of the several uses, we have classified the five major uses. The first is the spatial analysis. Here, grids provide a structural framework for performing various spatial analysis, such as overlay operations, proximity analysis, and interpolation. The second use is data representation. Whenever we have a raster grid, we use it to represent a continuous spatial phenomena, like for example elevation or temperature or satellite imaging. The third use is having a map display. Now grids help us in providing a reference system for displaying geographic features on a map. So the map display can be done very easily using grids in a GIS. The fourth use is modeling and simulation. So grid-based models are used to simulate and analyze spatial processes like hydrological modeling, terrain analysis, and ecological modeling. The fifth and the last use of grids that we have classified is georeferencing. So this is very common, and I'm sure you are using it as well by this time. So grids are used to assign geographic coordinates to a specific point or to many other points, allowing you for a precise location identification on real world in your digital data model. So overall, we can say that grids play a crucial role in GIS as they provide a structural framework for organizing and analyzing spatial data. So what it does, it enables a wide range of application in different fields like environmental science, urban planning, natural resource management, and many more. Next, we come to the attributes. So, whenever we are trying to define an object attribute, it is associated with several factors. So, here we are trying to understand that heights are treated as attributes. Like I told you, that whenever you are defining your basis of vector models based on your points, lines, and grids, it is 0, 1, and 2 dimensional object identifiers, but whenever you go to the third object, it doesn't have a separate entity, right? It is an attribute, it is not a separate entity. It is based on your two-dimensional uh, parameter, but it does not have a separate entity. So heights here are treated as attributes to the objects, but not as a part of the geometry in layer based data model. So object attributes have two features. First, they are the same as the entity attributes of the real world model, and the second is that they are stored in tables with objects or lines and attributes in columns. So these attributes provide context and additional details about the geographic features represented in GIS dataset. Now, the combination of spatial geometry and attribute data will only enable GIS analysts to perform different types of spatial analysis. It is not possible for you to have single spatial geometry or just the attribute data. There always has to be a combination of both because they are incomplete without each other. Both these features of any object need to be present, and they also help you make informed decisions which are based both on the spatial and non-spatial aspects of the data. This is just a dummy representation of your attribute in the form of tables. So you have seen a lot of examples before, so I will not get into too much of details of it. So this is like another example of your attribute representation in the form of table. So this one comes from the land cover of a residential zone. So there every land parcel has been given an ID by the user. They have also zoned it as residential. Then they have given the address of each point location that they have marked in their land use zone. They also have mentioned the zip codes of the region, like where different houses are being surveyed. Then they have also mentioned the state and the tax region, which region do their taxes go to. So this is like a very detailed attribute table. It can be more detailed or it can have lesser information as well. So here are some of the common examples of object attributes in GIS. So you have a name or identifier that identifies your data set. Then you have a type or category of your object or your entity. Then there is text or descriptive information. For example, the zoning part, it's a text or descriptive information. Or your address part, it is also a text or descriptive information. I am so sorry, the category type is going to be your zoning, not, although it falls in both the categories, but it will be more appropriate to call zoning as a uh, category type rather than a descriptive information. Your address is your descriptive information. Then you have boolean yes or no values. Okay, for example, whether this particular house has trees or not, whether it has parking or not. So you may or may not have your boolean values. Then you have categorical data. You also have multimedia or hyperlinks. Someone can provide a link to the Google map that will point you on the app itself where this particular house is located. So there can be another column that has hyperlinks or multimedia. Then you have spatial relationship, network connectivity, address information, which is here, ownership or administrative information. For example, administrative information can be your postal code or zip code. It can also be your state. Okay, so this postal code is more specific as compared to state, because postal codes vary within a state. Now we finally come to the summary of today's lecture and this session. So what have we tried to understand? We have tried to understand that a real world model reduces complexity. A real world model is also connected to data and it becomes a database, right? So you connect uh, the reality with the virtual form of data that you have and you make it a database. The carrier of information in data models are also known as your objects, and each object characteristics are comprised of its type, attributes, relations, geometry, and quality, right? Then we have a data model design. We have tried to discuss a very general layout of your data model design, how it comprises of different graphical representations in the form of points, lines, and polygons. Then we have understood object attributes in more detail. And in the next session, we shall discuss object relationships and shortcomings of GIS model. I hope this session is useful to you. If you just try to take a look at this image on your right hand side, this is a hierarchy uh, of your model. This again is a relation of your model, how different attributes are connected to each other. This is object oriented model, how different object types are linked to one another. So this is again a form of representing your GIS data when you are maybe trying to report it in papers for your final compilation of work. So I hope this was an insightful session for you, and we will meet again in the next class. If you have any questions, you can ask. I also believe that you had a live session with Sir. I hope that was also fruitful for you. If you have any carry forward questions from the previous session or from Sir's live session, you can ask that as well. You can also drop me an email regarding the same. So for now, I think I will be closing the session. Thank you so much for joining. I will see you in the next session. কেউ কিছু ভালো জিনিস খেয়েছে তাদের, কেউ কিছু ভালো জিনিস খেয়েছে তাদের। হ্যাঁ, সিঙ্গারা, মানে বাইরের থেকে এলে গন্ধটা পেয়েছি আমি।